Hello everyone, I'm Yang Peizhong. It's my pleasure to present our work. There are six main aspects to my presentation. Firstly, we introduce the special collocation pattern. A collocation pattern is a group of special features whose instances are frequently appearing together in geography. Collocation pattern meaning is particularly valuable for discovering special dependencies, and it may yield important insights for many applications. Next, we introduce the problem definition of collocation pattern meaning. Given a special dataset with special features and instances, the objective of collocation pattern meaning is to discover all prevalent collocations whose participation index no smaller than the prevalence threshold. The participation index is defined based on the table instance. Figure 1 shows a special dataset with neighbor relationships and the table instance of pattern ABC. The participation index satisfies the anti-Merton property, which can be used to reduce the search space. Unfortunately, meaning collocation patterns from massive spatial dataset is still challenging, since the number of potential patterns is huge and the participation index calculation is difficult. To address these problems, we propose a novel parallel algorithm based on neighbor dependency partition and column calculation. In this parallel algorithm, we firstly present the parallel methods based on neighbor dependency partitions and propose the column-based calculation approach for participation index. Two pruning strategies are designed to prune non-prevalent candidates. Last, we implement the parallel algorithm on MapReduce platform. In order to parallelize the meaning task, we divide neighbor relationships into different partitions, then perform the meaning subtask on each partition in parallel and summarize the meaning results from each partition. Specifically, we use the neighbor set of instance to materialize the neighbor relationships. Then the prefix future of instance is defined. Based on the prefix future of instance, we present the partition method and define the neighbor dependency partition. Given a special future f and its neighbor dependency partition, we prove that collocations starting with future f can be discovered from its neighbor dependency partition quickly. For example, Table 1 shows the neighbor database, and Table 2 shows the partition of future A. We can find all collocations starting with A in the partition centered on future A. Also, most collocation meaning algorithms can be used on each partition, but most are time-consuming, since they calculate the participation index by generating the table instance. But the generation of table instance is difficult. Actually, the table instance is not necessary for the participation index calculation. In this example dataset, there are 4 row instances of pattern ABC, but the 2 row instances in the red box are enough, because they contain all instances per feature appearing in the table instance. Thus, we propose the column calculation method to calculate the participation index without generating table instance. We define the participating instance and change the way of participation index calculation. Next, searching for the participating instance becomes the key. To find the participating instance per feature firstly, We prove that the participating instance satisfies the downward content property. Based on this, we define the candidate participating instances of a feature, which can narrow the search space of instances per feature. Then we need to verify whether the candidate instances are the true participating instance. To find a row instance including the candidate instance O, we firstly define the row instance search space of instance O, which can reduce the possible instance combination, and then the backtracking algorithm is used for the search process. Moreover, a heuristic strategy is given for verifying all candidate instances by searching last instance combination. Now we have addressed the two problems mentioned earlier. To further reduce the search space of candidates on each partition, we designed the pruning strategy. At first, we define the expandable instance and the expandable rate of a feature, and prove that the expandable rate of a feature is the upper bound of its participation ratio. Based on this, two pruning strategies are there. The proposed parallel approach is implemented on MapReduce platform. The first MapReduce job transforms the neighbor relationships into the neighbor database. The second MapReduce job divides the neighbor database into multiple neighbor dependency partitions and performs the meaning task on different partitions in parallel. It is easy to prove that this parallel algorithm is correct and complete. Besides, we also discuss its complexity. At last, we conduct experiments on real and synthetic datasets to verify the performance of the proposed approach. In experiments, the serial algorithms are implemented in Java. The parallel algorithms are implemented in Spark RDD and run on a Spark cluster with one master node and 10 work nodes. First, we show the superiority of the column calculation method compared with the traditional method based on table instance. We name the bottom-up meaning algorithm based on column calculation as CPM-CC. For comparison, generalized and expiatory algorithms are used as the baseline. Figure 2 shows the running time of three algorithms on the planned dataset. CPM-CC is faster than other baseline algorithms under different threshold settings. Figure 3 shows the space consumption, and the CPM-CC is more space-saving than other two baselines. CPM-CC does not need to generate and save table instances, so it has better performance. Second, we show the performance of the proposed parallel algorithm PCPM and PCC with other two parallel algorithms. Figure 4 shows the result on Beijing POI dataset. PCPM and PCC shows better performance, especially when the distance threshold is larger or the prevalence threshold is smaller. Moreover, similar experiments are performed on a larger synthetic dataset. As shown in Figure 5, we can find that the superiority of PCPM and PCC is more obvious. Third, we tested the scalability of three parallel algorithms on synthetic datasets. Figure 6 shows the impact of the number of instances and the number of features on the performance of three algorithms. PCPM and DPCC always keeps the best performance. Besides, when the number of instances and the number of features are larger, its advantage is more obvious. Last, we tested the speed up of PCPM and DPCC on Beijing POI dataset and a synthetic dataset, as shown in Figure 7. For the same main task, the running time of PCPM and DPCC is reduced by increasing the number of worker nodes. Moreover, adding work nodes is more effective for enhancing the performance on the synthetic dataset with more features and instances. Finally, we make a conclusion for this work. A parallel approach is proposed for collocation path meaning, and we designed the column-based method to improve the prevalence calculation. Moreover, two training strategies are proposed to narrow the search space of collocations. The proposed parallel algorithm is implemented on MapReduce platform, and we conduct extensive experiments to verify its performance. That's all. Thank you.